Okay. Hey guys, good morning.
Morning,
Right.
sir.
So we'll wait for a few more minutes. Let your friends join. Okay, guys, in another minute, we'll start. Okay, so I think we'll start and share my screen. Oops, whole host disabled. Participant screen sharing. Oh my god, wait. Do okay, just a moment. They have to make me host, and then only I can share the screen. Just a moment. Hello. And the host மட்டும் ஆக்கி விட்டீங்கன்னா I can share my screen. Yeah, thank you. Oh yes, now I'm the host. Now I'll be able to share my screen. Okay, fine. I'll start right away. Okay, able to see my screen, I hope. I just flip my laptop. 1 second. Okay, hope it's still going on. Yeah, cool. One second, people. Right. So we have been doing chemical bonding, if you can remember, right? So we finished all the basics. We saw Lewis theory with valence bond theory, right? So we saw what were the problems they were facing, right? What they were not able to explain, valence bond theory and your Lewis theory. So in your Lewis theory, the main problem was there were compounds which were having more than 8 electrons in the valence shell, less than 8 electrons in the valence shell, right? So, but your Lewis theory is predominantly based on octet or duplet rule, right? So, and when I go for valence bond theory, right? So it said that when a chemical bond, a covalent bond is formed when the unpaired electrons in the valence orbitals of the atoms gets paired. As simple as that. When the unpaired electrons comes together to get paired, right? So how are they going to get paired? They're going to come and get paired by the means of overlap of orbitals, right? Okay, so yeah, for most of the compounds it worked, right? But for carbon compounds and some other compounds, right, according to that, I can have only 2 bonds for carbon, but what I see in reality is I have 4 bonds in all of the compounds which contains carbon, right? So these were the problems we faced with valence bond theory and your Lewis theory. So went on to the next level, right? That is your theory of hybridization and VSEPR, right? So theory of hybridization just talks about how a covalent bond is formed and all that. And VSEPR is going to help me find out what is the structure of the molecule, right? Okay. So in theory of hybridization, I told you the atomic orbitals are going to come together to form something called as hybrid orbitals, but not randomly, right? The conditions are that the number of atomic orbitals combining, right, should be equal to the number of hybrid orbitals formed, right? And also that the orbitals involving in the hybridization should be of comparable energy. You cannot say, if you want to make sp3 hybridization, you cannot take 2s orbital and 4p orbital. No, that's not how you do it, right? So I can have 2s and 2p, or say 3s and 3p, or something 3s 3p and 3d. Like say the comparable energy orbitals can only be combined to form hybrid orbitals, right? And then when I went on to see VSCPR, right, it's just that it's going to give me the structure based on minimum repulsions between electrons, and we know there are only two types of electron. One is the bonding electrons and the lone pair of electrons, and we know which is higher, which is lesser. So based on that, we discussed how are we going to determine the shapes and geometries. So again, there is a difference between shape and geometry. In geometry, we just include the lone pairs without changing the structure, but your shape is the consequence of having the lone pairs in the geometry, right? So like basically the presence of lone pair or without the presence of lone pair, the geometry of a molecule is going to be same, right? But the shape might be different. So these are things which we saw, and then we started with steric number 2, steric, and then we see the linear shape, and then so went on. So we went on to see until I think we saw till steric number 5. Is that correct?
Yes, sir.
Right. Okay. So we should have seen till steric number 7, hopefully. Sorry, steric number 5, hopefully. Right. So is there anyone who want to ask me something from previous classes? So this is the overview of what we saw till now in this chapter. Right. Okay. So we'll continue. Right. Fine. Cool. So I think the last molecule which we discussed was I3 minus, if I can remember, right? So I3 minus came under the this thing of AB2L3, again steric number 5, right? So now obviously if you look at this, I have steric number 5. The moment I see steric number 5, the geometry is fixed. What is the geometry?
Trigonal bipyramidal.
Yeah, TBP geometry, trigonal bipyramidal geometry. So in trigonal bipyramidal geometry, I have to put 2 bonding atoms and 3 lone pairs, and I think we saw some rules for that. What is the name of the rule?
Benz rule.
Yeah, bent rule, right? So bent rule is for 2 of the things. One is for okay, bent rule is exclusively only for what is that? Trigonal bipyramidal geometry, right? So if I have all of them to be bonding atoms, and if it is going to be unsymmetric, right? Say in the case of PCl3F2, something like that, right? So I told you the bent rule says that you have to put the more electronegative atom at the axial position, right? And when you have lone pairs in the trigonal bipyramidal geometry, they have to go to the equatorial position. So higher electronegative atom to the axial position, lone pair to the equatorial position. So whenever you have this, obviously I found out when you put the 3 lone pairs in the 3 equatorial position possible, so the bonding atoms will be at the axial positions, making the shape to be linear. Yes, right? So this is what we saw, I think, last before we wind up the class, right? Okay, so today we'll start with steric number 6, right? Fine. So steric number 6, obviously I know the hybridization would be sp3d2. Yeah, sp3d2, right? say the first type of molecule which I want to take is AB6. That is no lone pairs, all six bonding atoms, right? So the perfect example could be SF6. I see guys, hope you have the table with you, right? So again, just start filling the table as we discuss, right? That's mandatory. If you don't have the table with you, you will not be able to just go back and just check what and all we did. Anyways, right? So fine. So now I have to make sure that I have six bonding atoms and their electrons must be placed as far away from each other, right? Now, what is the shape or what is the geometry?
Octahedral.
Yeah, right. The geometry is going to be octahedral. So this is how it looks, right? So bonding atom, bonding atom, bonding atom, B, 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 right? Fine. Maybe like my drawing maybe tells you that the bond lengths are different, but it's not all the bond lengths are same, right? Okay. So this shape can also be called as, like if I forget me this particular part, wait, I can just draw it again if you want. Right. So if you look at this particular shape or geometry, right, this is octahedral. Obviously, the shape here is what is called as octahedral shape, right? There is one more name also which can be given to this. Any idea what is that name?
Sir, is it square
Sorry,
bipyramid? Square bipyramidal.
I'm not able to hear you, Kana.
So can you?
Why am I not able to hear you? In the chat, maybe. What the octahedral can also be called as? Yeah, square bipyramidal. Yes, that's the thing, right? So yes, Harini, you were right. Right. Okay. So yes, you can see from here. So you can see there's a square, right? And bottom, I mean top one pyramid, bottom one pyramid. So it is can also be called as square bipyramidal. Okay, fine. I think there is a problem in that particular surface. Anyways, right? So it's called square bipyramidal shape. Right. Okay. So that's about SF6. I mean, AB6 kind of molecule. And obviously, the bond angle, if you check all the bond angle, this, every bond angle here will be 90 degrees. Okay. All the bond angles there would be 90 degrees. Okay. Fine. So this is about steric number 6. And the type of the molecule is going to be AB6. Is that cool? Right. So now we'll move on to the next type in steric number 6 itself. Let me add a page. Right. So next thing I'll take is say AB5L. Right. Okay. There's going to be one lone pair. Right. Cool. Now there is since now I don't have this complication with just trigonal bipyramidal geometry. There is no axial. There is no equatorial. All bonds are same. Right. So there is no restriction. You can put the lone pair anywhere you want. Right. But if you want to visualize the shape of the molecule, again, geometry is TBP, no doubt. Right? In TP, sorry, I'm really sorry, it's not TVP, it's octahedral, right? So geometry is still octahedral, right? So how, like if you want to visualize the shape of the molecule, this is how we visualize. So I have, right? So I have 5 bonding atoms, right? And there is one lone pair, right? Or let me put the, oops, wait. Why did I change? No, I don't want green. I want only black. Okay. Right. So let me change. Oops. Okay. So maybe let me put the lone pair bonding atom up and the lone pair down. Okay. Fine. So now again, how will you bring about the shape of the molecule? Just forget that the lone pair is there. Just forget that this is there. Right. And what you see is basically going to be a square with a single pyramid. There's only one pyramid at the top. So we don't consider the lone pair as this position whenever you go for shape. Right. So AB5L, this is how the geometry looks. And if you just consider, I mean, don't consider the lone pair, the shape will come out to be square pyramid, right? Square pyramid, very simple, right? Okay, so that's okay. Any examples for this molecule? Maybe in the chat. Any examples for the molecule AB5L?
Sir, CLFI. Sir,
Sorry?
CLF5.
Yeah, I think CLFI should work. Yeah, absolutely it works. Yes, right? So CLF5 is a very good example, right? So CLF, sorry, F5, right? So again, you can check for chlorine. I have totally 7 valence electrons. Out of them, 5 are involving in bonding. So there is 2 electrons left out, and that corresponds to 1 lone pair, right? Okay, so obviously CLF5 will fit this AB5L type of molecule, right? Okay, so this is okay, fine for us. Cool. So that is about AB5L. We'll move on. Right, next I can go for AB4L2. There are 2 lone pairs, right? Actually, I forgot one small thing, guys. Let me go back to. We'll come back to this. Let me go back for your AB6. Okay, so what I forgot there is, say if you have SF6, that means if you have a symmetrical molecule, there is no problem, right? But if you have an unsymmetrical molecule, say I have SF4Cl2, something like this, right? Now, how will I go about the geometry? Where should I place the fluorine atoms? Where should I place the chlorine atoms? That's the question, right? You have to be very like you don't have to be very careful. It's pretty easy, right? So what you have to do is that whichever are the 2 dissimilar atoms, right? Obviously in this case it's chlorine, right? 2 chlorine atoms are there, right? Whichever are the dissimilar atoms, just put them at the corners of the octahedron. In the sense, the opposite corners of the octahedron. In the sense that, say sulfur, I'll just make the bonds. Okay, so you can put fluorine atoms anywhere, but the probabilities of you, where should you put the chlorine atoms, is that, say you can put the chlorine atoms here and here. See, you can understand what I'm trying to say. You should put them in the opposite corners of the octahedron. So the one of the question is this, or say I can put the chlorine atoms like this, vertically opposite, right? Or you can put the chlorine atom here and here, right? So this also you should remember. Whenever you have dissimilar atoms, right? So make sure that they are placed in the opposite corners of the octahedron. Okay, right? So this also you remember. Now we'll come back to AB4L2. Now same thing what we saw now is going to work there, right? So in like, okay, so let me, if I draw the, right? So now I'll put the bonding atoms like this, right? Now I have 2 lone pairs to consider, and how it works for dissimilar atoms, how you put them in the opposite corners of the octahedron. Just like that, you put the lone pairs in the opposite corners of the octahedron. This is your geometry, right? Okay, now if I want to consider the shape, again the same thing, just forget that this lone pair and this lone pair exist. Just forget that. And what shape do you see?
Square planar.
Yes, absolutely, right? So if you don't consider the lone pairs, you just see a square, right? So the shape of AB4L2 is square planar. That's very simple, very simple, right? Okay, so again, any examples for this?
ZeF4.
So what is it?
ZEF4. XEF4.
ZEX. Ah,
XE.
oh, okay. Yeah, XEF4 is a good example, right? So XEF4, xenon tetrafluoride, right? So again, xenon has 8 valence electrons, 4 are involving in bonding, so 4 electrons are left out. So obviously this corresponds to 2 lone pairs. Very simple, right? So it fits the thing. I have 4 bonding atoms, 4 fluorine atoms, and 2 lone pairs, making it fit AB4L2. Cool, right? Fine. So that's about steric number 6, people. You don't have anything other any other case other than this. You don't have AB3L3. You don't have AB say AB2L4. All those things are not there. Okay, so don't worry about it. Right. So you have only 3. Right. So I have AB6, AB5L, and AB4L2. Very simple. Cool. Right. So last we have to go for steric number 7, which is very rare, obviously. Right. So steric number 7, right? Again, under this, the first type of molecule is AB7, right? Okay. So if you look at the hybridization is sp3d3, right? So please understand this is very rare. Okay. Again, AB7 is itself is rare. I'm going to give you AB6L also. That is like what to say, atrociously rare. Right. Okay, so anyways, so what can be examples? The best example I can give you is IF7, right? IF7 is a very good example. Okay, so the shape and the geometry in this case is going to be this, right? So it's okay. I'll tell you the shape, and then you will actually draw what how the structure is going to look. The name of the shape, it's called pentagonal bipyramidal. Right? The shape is going to be called as pentagonal bipyramidal. I think now you'll be able to draw the structure by yourself, but still I'll draw. So you put just A in between, and then you draw a pentagon. Okay, done. So now you join all the corners, or wait, okay, you in all the corners you put the bonding atoms B, 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 and your B. Right? So 5 are over. Have to go account for 2 more, and it says from the shape, I mean from the name itself, it's going to be a pyramid. One at the top, one at the bottom. So one at the top, one at the bottom. Just join all of them. Right? Very simple. So you have a pentagon with 2 pyramids, one at the top, one at the bottom. So that's how it's going to be pentagonal bipyramidal. Easy. Right? Okay. Now last in this itself, as I told you, I can have AB6L. Okay, any examples for AB6L? Any examples? Any which you can think of?
ZEF6.
Sorry?
XEF6.
Yeah, XEF6 will work. Yes. XEF6. So again, you can see obviously if you calculate, you'll have 6 bonding atoms and one lone pair. Basically, xenon has 8 valence electrons, 6 are involving in bonding, and 2 electrons are left out, 1 lone pair. So again, so that is how, I mean, this is the example for AB6L, right? Now the shape is the thing, right? The geometry is again pentagonal bipyramidal, right? But the shape, I like we don't have to look at the shape. We just have to know the name of the shape, and the name of the shape is distorted octahedron. Right? The shape, excuse me, right? The shape is called as distorted octahedral shape. Okay, so you can understand what is it. An octahedral shape would have been there if it's just AB6, but since I have the presence of this lone pair, right, the octahedral is distorted. So it's not a regular shape. That's what you need to understand, and you don't have to know the shape. Forget it. right? You just have to know the name of the shape, that is distorted octahedral shape. Is that cool? Right?
Yes, sir.
Fine. So that's it. We have completed your what is it? We have completed your VACPR and theory of hybridization. That's it. Okay. Right. Fine. Now that you know the shapes and geometries and where to place the lone pairs and all those stuffs, right? Now we can actually look into a physical phenomena called dipole moment. Okay. So obviously you should have learned about this. You should have heard at least the term. What is this dipole moment and stuff, right? Fine. So let me go through, take you to the, take you to the basics, right? So when I say dipole, right? When I say dipole in chemistry or obviously in physics, right? What I know about, what I can say about it is that it is equal and opposite charges, right? It is equal and opposite charges separated by a distance, right? So you have charges, right, which are equal and opposite, right? And they are going to be separated by some distance. Right? That arrangement is what is called as your dipole. Okay, so something like this, say plus q, some in some distance I have minus q, and the distance between them say is d. This entire arrangement is what is called as your dipole. Okay, right. Now what the next thing is, what do you mean by dipole moment? Right, now dipole moment is a mathematical thing, right? So it's very pretty simple. Dipole moment is denoted by the letter mu, right? So I can write mu as q into d. Very, very simple, right? I think you should have been learning it so much in physics. Now that you should have completed your portions, this is not a big deal for you. Anyways, right? So you take the magnitude of charge and you take the distance and you multiply them, and that product is what is called as my dipole moment. Okay, so anyways, we are not interested in this mathematically, this thing. So for different compounds, right, how will I be able to compare what is the dipole moment? That's what we are interested in. Okay, right, fine. So obviously you can what you can understand here is I have to have, first of all, development of charges. Obviously that is the most important thing. So you can tell that in case of ionic compounds, right, in case I have the positive charge and a negative charge, obviously that's exactly what happens in an ionic compound. Ionic compounds will have generally high dipole moments, no doubt about it, right? But how to say, like, see, if you look at a crystal, you used to finish all its solid state, you know how an ionic crystal will look, right? So obviously it will be plus minus plus minus plus minus, alternative plus and minus in the 3D. Like it can even come above the computer screen, it can go below the computer screen, right? So this is how the this is how the crystal looks. The lattice, I would say, the perfect word for me to use is lattice, right? So this is how the lattice looks, right? So what happens is, one more thing I'll tell you, that this dipole moment is a vector quantity, right? That means whenever you have basically, we know that it is going to have magnitude as well as direction, right? So you have to go for the vector, like you have to go for the vector addition of dipole moments. If you have individual dipole moments present, say I would say between this positive charge and this negative charge, I'll have a dipole moment. Again, say between this and this, this and this, this and this. So that's how it's gonna be, right? And obviously from this side also, it will come from this side towards you, about what is it, away from you, right? So all these things are gonna get cancelled. That's what happens in a crystal, right? And if you can isolate, if you can isolate a positive charge and a negative charge alone, only two of them are there, yes, definitely they will have some dipole moment. Okay, right? But in a crystal, in a lattice, no, there is not going to be any dipole moment, because all the things are going to get cancelled out. As I told you, that dipole moment is going to be a vector, right? So all the vector sum will lead to zero dipole moment in a crystal, right? But if you can isolate one cation and one anion, yes, absolutely true. I'm going to have some good amount of dipole moment, very high amount of dipole moment, right? But again, we are not going to speak for ionic compounds. We are going to speak dipole moments for covalent compounds, right? Because from the structures, right, obviously you will be able to understand, or it is pretty more what to say, significant with the dipole moment in your uh, covalent compounds. Okay, fine. So we'll just go about it. Right. So what we saw from there is that I require charges, right? So in covalent compounds, I know there is definitely not going to be full charge, right? But due to certain things, right, I can have development of partial charges, right? So can you tell me what are those kinds of compounds which have partial charges?
Polar.
Obviously, right? So it's called polar compound. So obviously, right, so it's pretty much straightforward that you can have dipole moment only in polar compounds, not in non-polar. Obviously in H2 there is nothing, in Cl2 again there is nothing, right? So obviously you need to have that at least one polar bond should be there. That is the first criteria, but again that is not the only criteria. Okay, so first of all, I need to have a polar bond. So for example, if I have HCl molecule, absolutely yes, like you can see there is a difference in electronegativity. Chlorine is highly electronegative, hydrogen is not. So you can see that there is going to be del negative developed here, partial negative and partial positive. And obviously they'll be separated by distance of their bond length, right? So I mean the distance of separation we are speaking about here is the bond length. So obviously the magnitude of this and this are going to be same, except that one will be negative, another will be positive, right? So obviously this will be able to have higher dipole moment. Okay, now if I ask you, I have HCl and say if I have HF, which do you think will have more dipole moment?
HF.
HF.
Sorry.
HF, sir.
HF.
Yeah, HF, right? So you can, okay, again now for this at least you must remember the formula. It's Q into D, right? So if I call it as del 1 and here it is del 2 plus and del 2 minus, right? So obviously wherever I'm going to have like maybe, okay, maybe you can talk in terms of bond length, the D, if you speak, right? So obviously in case of HF, I have smaller bond length, right? Because fluorine atom is small, hydrogen atom is small. The bond length in HF is little small, right? Obviously HCl will have higher bond length, right? But please remember, always remember, the bond length, we are not going to take it into the picture. Even if even if you're going to take it in the picture, they are not going to have significant effects on the dipole moment value. Okay, so whenever they ask you a question, whenever they ask you to compare this dipole moments of different molecules, you just compare only the Q, only the charge value, right? Do not much worry about your bond lengths. Basically in chemical compounds, with the distance of separation is their bond lengths, right? So you don't have to worry much about them, because what I can understand is, say this will be some like this is giving you an approximate value, not even approximate, some random value. Say HCl, I can say that, say it is 1 nanometer. I didn't even know it's correct. I'm just giving you a value. Say this can be some 1.2 nanometer. I mean, it should be lesser than this. So I can say that it can be, say, 0.8 nanometer, right? So in nanometer scale, having a difference of 0.2 is really not going to have much effect on the difference in dipole moments, right? But if you look at the charges values, del 1 and del 2 is way higher than del 1, right? Obviously the reasons are obvious, right? Because fluorine is more electronegative than chlorine, right? So the charge separation also is going to be more towards fluorine and less towards hydrogen than in the case of hydrogen and chlorine, right? So obviously HF will have more dipole moment than HCl, right? This is understood. Okay, fine. Now let us make us complex. Okay, say, uh, okay, now I'll give you an example. Now that we understood, okay, we understood how are we going to go about dipole moments, right? Now I told you that having polar compounds, sorry, I would say having polar bonds is not the only criteria, right? Okay, now why is it like this? Because say if I give you an example, that's the best way I can put it. Say if I have CO2 molecule, okay, if I take CO2 molecule, oh wait, and I forgot one more thing. let me go back to the previous page. I'm sorry, guys. I think that page is gone. Okay. I'll tell you. I'll tell you one more thing, right? So we told that dipole moment is a vector quantity, and its formula is equal to mu q into d. All that I told you. If it is a vector quantity, what you have to understand is which direction it will point towards. Okay. Now, please understand dipole moment. The direction will always point towards the more electronegative atom. Or, and also I can also say that it is going to point towards a direction where there is high electron density. Okay, so please keep this in mind. It's very, very important. Okay, so what, like, we know magnitude is this q into d, very simple. But what is the direction of dipole moment? The dipole moment is going to point towards more electronegative atom. Obviously you can see this is where I have more electron density, this is where I have more electron density, right? Or obviously in terms of the electron density, because the electronegative element is going to pull the electron towards itself. Now, why did I mention this specifically is that when you have lone pairs, right, they also will have some dipole moments, right? We'll see about it, don't worry, right? So in that case, obviously you have to point the dipole moment towards the lone pair, wherever the lone pair is present. Okay, so don't worry. Anyways, cool. So we'll move on. So looking at this molecule CO2, yes, I do have a polar bond. Obviously, you can see that CO bond, C double bond O, or C single bond O, whatever it is, I have considerable difference in electronegativity. Yes, the bond is polar, no doubt, right? But if I, now obviously you can say that there are two CO bonds here and here, right? Both of them will have some dipole moments, right? And as I told you, you have to go for the vector sum of this, right? Now, if you go for the vector sum of this, now you have to know what is the direction of the small direction of dipole moments in both these cases. As I told you, it should point towards the more electronegative atom. So for this bond, it is going to point towards this oxygen, the dipole moment. And obviously, in this case, it is going to point towards this oxygen atom, right? So what do you think? What is the end result now?
Net dipole moment is 0.
Yes, dipole moment is 0. Overall dipole moment for this molecule, mu, is 0. Okay, so what you understand from this is that just having polar bond is not sufficient, right? So the polar bonds, if you have multiple, if you have only one polar bond, no issues at all. Definitely that is going to have some dipole moment, right? But if you have more than one polar bond, right, now you actually go for the vector sum, and the vector sum should not turn out to be 0, right? Or if I can give you a small shortcut kind of stuff, but not a shortcut, but a logical thing. If you have a symmetrical molecule, whenever you have a symmetrical molecule, that will always going to have 0 dipole moment. Just remember this, right? Whenever you have a symmetrical, this is obviously symmetric, you can see a symmetry here, right? So whenever you have a symmetrical molecule, definitely that is going to have dipole moment to be 0. I can give you more examples, right? Say, let me take BF3 molecule, right? So again, I have a polar bond, but if you look at the shape, it's trigonal planar, right? So now what do you see? Now, obviously, if you look at the direction of dipole moments, this is the direction for the first dipole moment, this is the direction, and this is the direction, right? Now, again, this molecule is symmetrical, so I can say that this dipole moment is 0. But if you want to prove that it is going to be 0, what you have to do? You have to take the vector sum of this, correct, right? So you have F and F about 120-degree apart. You know how to calculate the vector sum, hopefully, right? So if at all for these two, if I want to calculate the vector sum, the magnitude, if I want to calculate, so hope you remember, it is wait, a squared plus b squared plus 2ab cos theta, not ab2, right? Oops. Right, so hope you remember, this is how you find the magnitude if you have two vectors, right, having say a and b as the values, right? So this is how you find your what is that resultant vectors is magnitude. Correct, right? So obviously if you put this here, you will see that this two, that is this and this together will give me a F, basically another F kind of thing here. So again, this and this will get cancelled out. Okay, hope you understand. If you're not able to understand, go for it properly. You know triangle law of vector addition, you know parallelogram law of vector addition. Just apply it here. You will understand that all the things are going to get cancelled out. Or in easier words, all this molecule is completely symmetrical, right? So obviously you can say that this is going to have a dipole moment of 0. Yes. Okay, fine. Now another case, like, okay, now we understood when what are, okay, when again when I have say CCl4, what happens? Again, it's a tetrahedral molecule. Again, it's going to be what is that? What is it? Symmetrical. So again, the mu value of this will be 0. Yes, right. But if I have CHCl3, right? If I have CHCl3, yes, I will have some considerable dipole moment, no doubt, right? Because one of the atom is dissimilar, right? So at that case, it is not symmetrical. So the mu is not equal to 0 in this case. So there will be considerable dipole moments here. Is that cool? Right? Okay. Now moving on, we'll just make it a little more interesting. Say I have BeCl F, okay, and say BeBr and F, okay. Right. Now comparing these two molecules, now I want to tell me which is going to have more dipole moment. So basically, if I have BeCl2, that will have 0 dipole moment because it's linear. That side is going to cancel this side, mu is 0. But for these two, definitely the dipole moment is not 0 because it is not exactly cancelling out. Right? Okay. Now think and tell me which is going to have a higher net dipole moment. Say I'll call this molecule 1, this molecule 2. So 1 or 2. Maybe you can put it in the chat box. We can take a vote share also.
2, sir.
Okay, so who said 2?
Siddharth.
Okay, Siddharth says 2. Fine. Okay, so 1 vote for 2. Anybody else?
Sir, show the molecule.
Yes?
Sir, show the molecule, no, sir.
Oh, yeah, sure. Why not? So yeah, this and this.
Sir, 1, sir.
Okay, so who is that? You're saying 1?
Srivatsan, sir.
Sorry, I'm not able to hear you, Kana.
Srivatsan, sir.
Oh, Srivatsan. Okay, so I have 1 vote for 1 and 2. See, okay, fine. So anybody else? Anybody wants to give a vote? Okay, 2. Akshay says 2. Harish also says 2. Yes? Why are the girls not responding? Yes. Okay, fine. So 1. Aditi says 1. Harini, still thinking. Okay, so Harini also says 1. Fine. Cool. So we'll see how to look at this. Fine. So if in this, obviously you can understand that there is going to be net dipole moment in both the cases, no doubt, right? Because if at all it was F and F or Cl and Cl, yes, they will, this and this side and this side will get cancelled out, no doubt. Correct. Okay. Now people, fine. Okay. So if I take this molecule, first one, right? So obviously the dipole moment is going to be towards chlorine and this dipole moment is going to be towards fluorine, no doubt. Okay, now they're in opposite directions, correct? Right now, okay, there is a considerable difference in electronegativity between B and Cl, right? And obviously there is greater electronegativity difference between beryllium and fluorine, right? So what I can say is that the overall dipole moment is actually going to point towards fluorine. Hope you understand, right? The individual dipole moments towards electronegative atoms, right? And obviously the overall dipole moment is going to point towards the higher electronegative atom, and that in the case is fluorine. So this would have been the direction of the overall dipole moment. In the same thing in this case also, the overall dipole moment is going to be towards fluorine, right? Now, which is going to be higher is the question, right? Now, let me put it this way. Okay, let me draw the molecule Cl F, right? Now, let me put it like this. Okay, I'll just draw a little smaller arrow for this and a very big arrow for this. Okay, right? So obviously the difference between these two, the difference between this and this would have been the direction towards this. Say the difference is little small, right? Because both fluorine is electronegative and chlorine is considerably highly electronegative, right? But if I take beryllium with Br and F on this side, right? Now with this, okay, let me rub the, okay. So this will be pretty less, like compared to this one, right? Compared to BeCl, BeBr will have a smaller dipole moment, and this is going to be same. This is going to be pretty big, right? The beryllium F is going to be pretty big, right? Now I have to take the difference between them. So obviously the difference is going to be higher, right, than this arrow. This arrow is going to be little bigger. Why? Because the subtraction happening here, okay, this is the thing, and from this is getting subtracted, right? So obviously the subtracted value is lesser than here. When I go, this is considerably high dipole moment, so the subtracted value is higher. Okay, so obviously the BeBr, that is the second molecule, will have higher dipole moment. I want everybody to give me a S, at least in the chat box, quickly.
Yes, sir.
Everybody understood or not? How second is having more dipole moment? Okay. Yes. Yes. Oh, Sanjana, I forgot. Sure, Aditi. I'll explain you again. No issues at all. Right? Okay. Let me see it again. Right, and maybe it's very clumsy. Let me add a page. Right? Okay. So what I'm telling is, say, let me take Cl, right? F. Okay, fine. So let me put some good things here. Fine. So this is the dipole moment this side, and this is the dipole moment this side, and I know the overall dipole moment is this. Okay. So now let me call it mu1 and mu2. Okay. Now here, what will be the net dipole moment? Mu2 minus mu1. Right? Okay. Now let me take the other one. Beryllium, Br, and F. Right? Say this is this side, this is this side. Say I'm going to call it as mu3. Right? Now let me still call it as mu2 only, because still it is B and F. Here also it's B and F, mu2, same. Right? Now the overall dipole moment is towards this side. So it is going to be mu2 minus mu3. Okay. Now what we have to consider is this along with this. Now mu2 is same. Right? Okay. Now which value will be higher from this mu2, right? In whichever case I subtract a lesser value. Say for example, if this mu1 was 5 and this mu1 was 3. So obviously whichever is subtracted lesser from mu2, from a huge part, whichever is lesser subtraction is happening, in that case I will have more dipole moment. Is it not? So obviously when I compare mu1 and mu3, obviously mu3 is lesser because it's Br, less electronegative, where chlorine is more electronegative, so more dipole moment will be there. So obviously subtracted value is lesser in this case. The higher in this case, and the subtracted value mu3 is lesser. So obviously the dipole moment of BeF and Br is higher. I think Shruti, is it okay now?
Yes, sir.
Shruti? Okay, cool. Very good, very good. Good. Right? So this way only you have to understand. Right? So this is how, like, even though you have polar bonds, you would compare two different molecules and then say it, right? Which is just having higher dipole moment, which is having lesser dipole moment. Cool, right? Fine. Okay. uh, Now, like, what happens is, generally they will not ask you to compare, right? Generally they'll not ask you to compare dipole moments of different molecules, except for this, what to say, these are some very easy cases. But if you go for complex structures, it will be very difficult, so they'll not ask you that. But what kind of questions they might ask you is, which of the following molecules is polar, something like that they'll ask, right? So when they ask you polar, they're not asking you about the polarity of the bond, they're asking you the overall polarity, in the sense the overall dipole moment, right? So if I ask you which of the following molecules are polar, the answer is whichever molecule is having some net dipole moment, that is the polar molecule, and rest of all the three options definitely will have zero dipole moment. Okay, for that you have to go for the net, what is that, the vector addition, all these things you have to go for it, right? Fine. And let me see some examples with lone pairs. Okay, fine. Now I'll take ammonia molecule, NH3. Okay, now I have ammonia molecule. Okay, now fine. Now there are going to be so many dipole, four. Okay, actually I told the answer, right? So they're going to be four individual dipole moments, right? Obviously, three NH bonds are there. And obviously, we know towards what the dipole moment is going to point. The dipole moment is going to point towards nitrogen, because that is what is more electronegative. So one dipole moment towards this side, another this side, another this side, right? Okay, these are the three dipole moments. And as I told you, even lone pairs will have their own dipole moments. Be very careful. So you have to put this thing towards the lone pair. So this is the fourth dipole moment. Okay, so 1, 2, 3, and 4. Four dipole moments. Okay, and obviously you have to go for the vector sum of this. And obviously, if you look at it, almost everything is in the same direction, right? So I'm going to have a very huge dipole moment for NH3, because all of them will add up. All four of these will add up, right? So you will have the net dipole moment to be very, very, very high. Is that cool? Right? Fine. So that's about ammonia. I want to have something like, yeah, H2 is H2 is again will be okay. H2 also we can see, right? H2O, if you look, there are two lone pairs, right? So this thing is like this thing is like this, right? And you can see that one thing is going to be like this, another thing is going to be like this. Okay, so you can okay, so what you can understand from this is that if I okay, when I talk about the lone pairs, this one, like, if I can change the color, maybe that will help, right? So this and this. Right, now what I'm going to do is I'm going to take the orange colors, and if I resolve them into vectors, right? If I go for the parallelogram law of addition, or whatever it is you want to do, you can do it. So what I can say now, one component will be this side, another component will be this side, same thing here, one component this side, the other component this side. So this and this gets cancelled, right? Again, but these two gets added up. Okay, same goes here. Like, I can put one this side, another this side, one this side, another this side, right? So again, you can see that this and this are going to get added up. Okay, so anyways, you can see that for H2O, there is some net dipole moment. See, and don't ask me, sir, will I be able to compare NH3 and H2O? The answer is yes, you can compare, right? And logically speaking, I can tell that H2O is going to have more dipole moment than NH3. Now, anybody wants to give me a reason why is it like that?
Sir, is it because it has more lone pairs?
Yes, absolutely true, right? Because H2O has two lone pairs, right? So one more thing is, comparing electronegative atoms with lone pairs have more effect on the dipole moment. Please remember this, right? Again, I repeat, when I have what is that, high electronegative atoms, and if I have lone pairs have higher effect on the dipole moment, on the separation of charges, because it's full electron density, right? So be aware of that. Okay, so H2O will have higher dipole moment than your NH3. Okay, fine. Now let me take some organic structures for the same, and we'll check that. Right? Say if I have, again, I can have 0 for molecules like this, right? So I can have actually 0 dipole moment for this. Why? Because again, it's going to be symmetrical, isn't it? Right? So again, what I can say, these two will resolve together to give me one OH here. So this OH and this OH again will get cancelled. You will have mu to be equal to 0. Yes. Okay. Now, fine. Now, what about this? Now, if I ask you to compare, this is a very good question. Actually, we'll take this. Okay. I have Cl or OH, however you want, you can keep it. Cl. Cl and Cl. Okay. Now say if I mark this as 1, 2, and 3, can you arrange these molecules 1, 2, and 3 in the order of their dipole moments? Okay, and just give me a minute. You put the answers in your chat and I'll be back in a minute. Okay. Okay, guys, I'm back. So hopefully there's something in the chat. Yeah, there is. Srivatsan, what do you mean by 2?
The 2 will have most.
Telling 2 is the highest or 2 is the lowest?
Most, sir.
Sorry?
Most, highest.
Oh, 2 is the highest. Okay, fine. Hey, just go for the rectangular components. That'll be the best useful. Like actually, the one thing is very easy. 3 is very easy. So this and this gets cancelled. Mu is 0 for this. So 3 is least, no doubt. Right? 3 is least. Okay, now the competition is between 1 and 2.
So 2 greater than 1, greater than 3, sir.
So 2 is greatest. That's what I'm telling. Okay,
Yes.
fine. Okay, any other answers? Three is lowest, yes. And Harini says 1 is the greatest. Okay. Fine. Aditi says 2 is greatest. Okay. Fine. Sanjana says 1 is the greatest. Okay. Fine. Okay. Fine. So we'll go. Okay. 1 is greatest. Siddharth is saying again. Harish tells me 2. Okay. Fine. So we'll check how are you going to do about it. Right. Maybe if I can change my color, it will be little black itself. I'll take, no issues. Right. So fine. Now this is no problem. Now this is going to point towards this side. Now if I take this chlorine, let me put the rectangular components like this. So one thing is pointing towards this side, the other thing is here, right? Okay. Now again, for this chlorine, no problem. For this chlorine, this is how the rectangular components will look. So what happens? This has some effect, obviously, right? This particular vector will have some effect again, but this and this will get cancelled out, isn't it? Right? This and this will get cancelled out, and the net result is only towards this side, very small, only half of this. That's how it is, right? But here I have one big dipole moment towards this side because this and this are getting added up, right? And obviously some cancelled dipole moment towards this side also. Okay, so obviously in this case it is getting cancelled, but in this case they're getting added up. So answer would be this: 1 greater than 2 greater than 3. Okay, this is a very famous question. So many times I have seen it coming in the exams, right? This chlorine all with OH, right? I have to be very careful with this, right? Easy 3 marks or whatever the number of marks it is, easy. Okay, you just have to go for the component separation and then just check, add or subtract, whatever it is happening. Okay, right? Cool. So that's about dipole moments, people, right? So I think you will be able to answer any type of question when dipole moment is going to be asked now, right? Okay, we'll move on. Right now, next thing what you have to see is about the bond angles, right? So again, there'll be good amount of questions coming from bond angle. They'll give you four compounds, right? And they ask them to ask you to arrange them in the order of bond angles. Okay, fine. So we already know when you don't have lone pairs. Now that thing is pretty straightforward. Like say if I have BCl2, BeCl2, I know it's going to be linear 180-degree bond angle. Say if I have BF3, I'm going to have 120. If I have CH4, it is going to be not 9 degree or not 9.5 degrees. So like whenever you don't have lone pairs, right? So the bond angles are pretty straightforward, right? But when you do have lone pairs, the system can get a little complicated. Okay, fine. So we are not going to look into what is that, your compounds which doesn't have lone pair, because that is pretty straightforward. But what I'm going to do is when I'm going to help you, right, to determine how or to help you find out what is the order or how do you compare the bond angles of two different molecules having lone pair. Is that cool? Right? And we are going to restrict our discussion only to say till steric number 4, not more than that. Okay, so if you're gonna go steric number 5 and stuff, it is going to be very complicated, right? So we will restrict our discussion only till steric number 4, right? Maximum till ammonia and ammonia derivatives. Now ammonia derivatives means not your organic compounds, right? The NF3, NCl3, something like that, or the group 15 elements, phosphorus compounds also. Anyways, so we'll go on about it, right? So let me do this. Okay, now let me just compare this. Okay, say I have NH3. Okay, and I have H2O. Okay, fine. Now I want to compare which is going to have higher bond angle, which is going to have lesser bond angle. Okay, now we'll see how this goes, right? Now in this molecule, there is an NH3, right? You have just lone pair, bond pair repulsions. Is it not? There is a lone pair, there is a bond pair. So I can have lone pair, bond pair repulsions. Okay, so because see, please understand, whenever you want to speak about bond angles, right, you have to always remember it is a bonding atom, central atom, bonding atom. So what I'm trying to tell you is a bonding atom, central atom, bonding atom. This bond angle only you'll speak. Same way, bonding atom, central atom, bonding atom. This is the bond angle. Okay, so please be very careful whenever you're choosing the bond angles. Okay, so central bonding atoms, central atom, bonding atom. That's the angle you should take. Okay, so fine. So in NH3, you have lone pair, bond pair repulsion. So what is going to happen because of that? So the lone pair and the bond pair are going to repel each other. So this is going to little more come down towards this. Is it not? The bond is going to get constricted. Okay, I think I have to, okay, maybe I'll open my video in some time, but anyway, it's not required now, right? So what you can understand is this is going to move towards this side and this is going to move towards this side. So the bond angle is going to get decreased. That's what you need to understand, right? Fine. Now here, if you have lone pair repulsion as well as lone pair bond pair repulsion, both the things you have, right? So obviously because of lone pair repulsion, they will move away from each other like this. Okay, the lone pairs will move away from each other like this in whatever directions I have put, right? And obviously because of that, I'm going to increase the repulsion between the lone pair bond pair also, right? So again, this is going to move towards this side, this is going to move towards this side, and the repulsions experienced here is pretty high than in this case. Okay, so now tell me, according to all the discussion which we had, which is going to have a higher bond angle? NH3 or H2O, which will have higher bond angle?
NH3.
Yeah, definitely, right? NH3 is going to have higher bond angle because there is little lesser repulsion there. There is only lone pair bond pair repulsion. So the little they are far away. So the restriction or the constriction in the bond angle is pretty less than in this case where I have lone pairs present. Lone pair repulsion will increase the distance between them, and thereby I'm going to decrease the distance between them. That is your lone pair bond pair. So what will the bond pair try to do? The bond pair will try to go still far away from each other than in this case. So there the bond angle is lesser. So I would say the bond, if you look at the actual values also, for H2O it is around 105 degrees, and for ammonia it is around some 107 degrees. Okay, so ammonia will have higher bond angle than H2O, no doubt. Okay, fine. Now this is okay. Now let me go for NH3 itself. I can have different this thing. 1 second. So let me take NH3 with NF3. Okay, so both the things are same geometry, same shape, everything is same, right? Except that instead of hydrogen, I have fluorine here. Okay, now how will you go about this kind of molecules is the question. What is the time? Yeah, we have 15 more minutes. Okay, so how will you go about this? Right, now what you can understand is people, these bonds which I have here, that is the NH bonds, are comparatively more polar than the NF bonds because the difference in electronegativity between the nitrogen and fluorine is not much. I mean, there is difference, but compare to the difference here, definitely there it is lesser. Between the NF bond, the polarity is lesser, right? So because of that, what is going to happen is the bond pairs you have here, you have 3 bond pairs you have here. So what is going to happen? These bond pairs are going to be more towards nitrogen. Is it not? Because nitrogen is more electronegative, the bond pairs will be more towards the nitrogen. Yes, I can draw it like this, right? I mean, putting it more towards the nitrogen and little away from the hydrogen atom, right? So because of this, what is going to happen? Now from the diagram itself, you can see the distance between the bond pairs are actually decreasing. Can I say that? Right? The distance, that is this distance I'm talking about, the distance between your bond pairs, between the NH bond pairs are decreasing because the bond pairs are moving towards nitrogen. Yes. Okay. So obviously what is going to happen here, if they're going to move towards each other, now the repulsions will increase. So definitely they will try to move away from each other. So the bond angle for NH3 is greater. Right, NH3 is greater because nothing of that sort is going to happen here, right? Because fluorine is more electronegative. So I would say even if fluorine is more electronegative, like it is going to be towards this, that means the distance is increasing, right? or I would say it is actually going to be in between, little almost in between. So there is not going to be much of an effect what you see here like this, right? Again, I repeat. Okay, so in case of NH3, right, since nitrogen is more electronegative, the bond pairs, these three bond pairs are going to be more towards your hydrogen, sorry, more towards your nitrogen, right? So this is how I'll be able to represent it, right? So what you see here, because of this movement of electrons, the distance between your bond pairs are decreasing, and whenever the distance decreases, the repulsion increases. So when repulsion increases, the bond angle will increase. They will try to move away from each other. That's what VACPR says, right? So he obviously, when I compare NH3 with NF3, so definitely NH3 will have higher bond angle because nothing of that sort is happening in case of your NF3. Is it okay? Right? Okay. Now let me ask you this question. Let me take one more example. Guys, understood how why NF3 is having higher bond angle than NH3? Please give me a yes in the chat box if you understood. Okay. 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 Fine. Almost everybody. Thank you. Thank you so much. Right. Fine. So now we will take maybe so NF3 with NCl3 will take. Okay, now we'll see how do you compare the bond angles. Now again, nothing of that sort is going to happen. Like what happened in NH3 is not going to happen for NF3 as well as NCl3, because again, the difference in electronegativity is not that much, right? But how can we go about it? How can we compare the bond angles? Let me draw it again. NF with the lone pair. Again, NCl, Cl, Cl with the lone pair. Okay, right. Now, how do I go about it? Now, what I can think about, right, is now you can understand that fluorines as well as the chlorines will have lone pair on them. Is it not? You will have basically three lone pairs on each of the fluorine atom, right? Each of the, again, here also 1, 2, 3, 4, 5, 6. Again, 1, 2, 3, 4, 5, 6. Anyways, so each of the hydrogen, sorry, each of the fluorine and the chlorine will have three lone pairs on them, right? Now you think and tell me, where will the lone pair interaction, again, actually, let me put it in a proper way, right? So you have two fluorines here and you have two chlorines here and here, right? Now, in which case, so what I'm trying to tell you is there is going to be some kind of interaction between the lone pair on this fluorine and the lone pair on this fluorine. Same way, the lone pair on this chlorine and the lone pair on this chlorine can interact. Okay, now you think and tell me in which case, whether in chlorine case the interaction will be higher or in fluorine case the interaction will be higher. You think and tell me. Just put in the chat box F or Cl, which will have more interaction between the lone pairs. F. Okay. Sriharni says F. See, I'm talking about the lone pair on one fluorine and the lone pair on other fluorine. Same way, lone pair on one chlorine, the lone pair on other chlorine. That interaction I'm talking about. What about others? Maybe it might be just a guess. I'm not. I see. Have I ever asked you? Please give me the explanation for what you're asking. All right. It's just a guess. Just type it here. F or Cl, which will have higher.
So what's the question again?
Oh, what's the question? I'm asking. You have lone pairs on two chlorines and lone pair. Okay, lone pair on two fluorine and lone pairs on two chlorines. Right. So I'm telling there is going to be some kind of interaction between this and the lone pair present on this fluorine. Same way, between this lone pair and this lone pair, I can have some interaction. So I'm asking where the interaction is higher, between chlorine-chlorine lone pairs or fluorine-fluorine lone pairs, which will have higher interaction. That's what I'm asking.
Okay, sir.
Okay, so Aditi says chlorine. Okay. Sanjana says F. Now guys are not responding. Hmm. Yeah, very good. Okay, so F. Srivatsan says F. Siddharth also says F. Okay, fine. Now let me ask you this. Like, I think this you cannot answer in the chat. Maybe you have to unmute yourself and ask. Answer. Right. Okay, guys, tell me what is the criteria you're thinking about? How do you say that it's F or Cl? What is that approach? What we have to do here?
Sir, I thought that the repulsive interaction between fluoride and fluorine will be greater
That's
because
what. Why?
fluorine is more electronegative.
Okay, fluorine is more electronic. There was something in the
Sir,
chat.
sir, I thought it was because
Ah,
smaller sized atom.
yes,
Something like
that's a good approach. No, right? That's a good approach. Yeah, okay, right? So talking about size is really something little logical. No, so obviously, so if the size is very small, right, and it is having lone pair, already they are very far away from each other, right? If it's very small, right, I would say this is a very diffused crowd. Since chlorine atom is little bigger, right, so the atoms can actually interact between them with a very far greater extent than in this case, because fluorine atom is very small, right? And even if I speak about electronegativity, right, even if I speak about electronegativity, what is electronegativity? Keeping the electrons to itself, isn't it? Now, and since fluorine is more electronegative, it wants to keep the electrons lone pairs with itself. It doesn't want it to interact. But chlorine, on the other hand, is little less electronegative. So it can, it's like fluorine is a very strict parent and your chlorine is little chill parent. Okay, he's just allowing his daughter or sons to do little whatever they want, but fluorine is very strict. It is going to have it with itself. Okay, so obviously the interaction between the chlorine lone pairs is going to be pretty high when compared to fluorine lone pairs. Two reasons. One, because fluorine is small and fluorine is more, and second reason to be fluorine is more electronegative. It is going to have the lone pair to itself. But chlorine's electron cloud is more diffused, again because of two reasons. One is because it's having higher size, and obviously because it is going to have what is that, lesser electronegativity, right? Okay, now that we understood this, I have the lone pair interactions between chlorine lone pair interaction is higher. Okay, now if that's the case, which will have higher bond angle? If the lone pair on chlorine and the lone pair on other chlorine is going to interact, which will have higher bond angle? NCl3 will have higher bond angle. Very simple. Yes, 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 yes. Correct, correct. Right. So obviously, since the lone pair interactions are higher, these bond will try to move far away. So NCl3 will have more bond angle than NF3. Is that cool? Right. So I think hope everybody understood whatever I'm trying to say. Right. Oops, what is this?
yes, sir.
Yeah. Okay. So one more example we'll take. Nothing. Okay, so let me take PCl3 with NCl3. Okay, this is the last question for today. Okay, because it's almost 8:25. Okay, so I want to compare what is the bond angle. I mean, how do you, which is going to have more bond angle, PCl3 or NCl3 is the question now, right? Okay, fine. So again, we'll draw the structures. And okay, so again, same shape, same geometry, everything is same except that the central atom is different, right? Okay, now, one second. I think I myself, uh, Okay. Yes. Fine. Fine. Now, what do you think? Which will have more bond angle? Now, see, it's the bonding atoms are same. Only central atom is different, right? So think about it and tell me which will have higher bond angle.
NCl3, sir.
Sorry,
NCl3, sir.
NCl3. Okay, fine. And you want to give me any reasons, Kana? Why is it like this?
Yes, sir, because N is more electronegative than P, no, sir.
Okay.
So then P and Cl interactions will be not as strong. So it will be easily pushed away by the lone pair.
Oh, see. Like the first point, what you told was correct. So obviously, nitrogen is more electronegative than phosphorus, right? Or I would say, in terms of size, if I speak, phosphorus is little bigger in size than your nitrogen, right? So now
Yes, sir.
tell me the lone pair bond pair interactions, and say the lone pair bond pair interactions, where it will be higher. In nitrogen case or phosphorus case? The lone pair bond pair interaction or repulsion, where it will be greater, in nitrogen or in phosphorus?
Oh, in nitrogen, sir.
Sorry.
In nitrogen, sir.
Okay, now how do you say that? Now see, it's all about, like last time what you saw, you had chlorine and fluorine. Since chlorine was little higher in size, so what happened? The interaction was increasing. Is it not? The interaction between these two was increasing, right? Now same I can say with this also, right? Phosphorus is little bigger, so it will have the electron cloud to be bigger, so the interactions are more probable here, right?
Sir,
But
Adha sir,
since
modale
nitrogen is
sonne.
less, yes, what is it?
Sir, Adha sir, modale sonne. That's confused item.
But what you said is the interaction for nitrogen is lesser. That's what you told. Like, until then, you were right. Absolutely right.
Yes, sir.
Okay, fine. Anyways, good. Anyway, if you told that exactly what I'm saying, absolutely good. Why not? Right. So, anyways, so what I'm telling is phosphorus is little bigger, right? So the electron cloud will be more diffused, and that it can interact more with your chlorine, right? But here, acid and nitrogen is more electronegative, and that means it is going to keep the lone pair to itself, and also it is small, so the interaction is pretty small, right? So where is the repulsion higher? Repulsion is higher in the PCl3. That means the repulsions are making the bond come closer. The bonds are coming closer here, the chlorine bonds, right? So obviously where I'm going to have higher bond angle, the higher bond angle is why I'm going to have an NCl3. Your answer is correct. I mean, and almost the explanation is also an 80% correct, but the last part only wrong. Yes. Okay.
Yes, sir.
Fine. So this is the answer. So NCl3 will have more bond angle than PCl3 because nitrogen is more electronegative and lesser size. So the lone pair bond pair interactions are lesser than in the case of PCl3, which will make the bonds come closer, decreasing the bond angle. Okay. Right. Now I told you so many things. And next class, I'm going to give you shortcuts to determine the bond angles. Okay, based on electronegativities, based on size, if it is going to be a central atom or a bonding atom, all these things will put some cases. Okay, and I'll give you the shortcut to find out the bond angles, to determine the order of bond angles. Okay, so I think we can stop with this for today. I think we'll again have a class on Saturday. So I think I will be most probably completing this chapter on by Sunday, most probably. Okay, right? Any questions you want to ask me? Yes, Srivatsan, NCl3 will have more bond angle. Okay. Okay, fine guys. You can take leave. We'll meet on Saturday. Right. Thank you so much.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.